Hi guys. So I think we can just start. Um, well, well. Uh, so yes. Okay. Uh, well, today I want to talk about Seq2Seq sequence-to-sequence model for net neural machine translation. So it's really popular task. Of course, we will talk about sequence-to-sequence approach. So it's like the base. It's like the baseline for this task, and I think everybody knows. So now today, um, such task can be solved by transformers, really great, and we will use transformer in our future seminars. But well, today we want to practice this approach and understand it. So because it based on recurrent neural networks. So, do you know something about sequence-to-sequence approach, like Seq2Seq models? Something about it? Something like maybe some. Did you read some articles or papers about it?
We had this topic last semester actually.
Okay, okay. So, well, you can see uh, you can see this pipeline of the sequence-to-sequence model. Yes, usually it's named like encoder-decoder models. Um, and why? Because we have like in the picture, yes, we have like encoder model with input on the one language. For example, here it's German language. Yes. Then we have some stacks of recurrent neural networks, for example, LSTM or vanilla RNN. Why not? So and then we have these Z bottleneck. It names like bottleneck. Yes. Um, and then we have like a decoder part, and these parts usually work like train like yes, on the output is the English text, yes, with some stacks of RNN2. So but with this bottleneck. So and of course, if you want to talk about sequence-to-sequence model, yes, they was very popular until 2017, until transformer models, yes, transformer architecture. So and if you used at that time Google Translator, yes, you can see that sequence-to-sequence work not so great. So sometimes Google Translator works not so accurately. Yes, like now. And this is why sequence-to-sequence have a very big problem in this part, so in this bottleneck, because just imagine, so you have a huge scope of text, yes, for example, several sentences. It can be like about 50 or even 100 words, yes, in total, and you have provide all these words in the encoder, and then move all information about these huge text, yes, about these 100 words, punctuation, the scope of text, yes, the grammar too. So you have to provide it to the coder through this bottleneck, this small bottleneck. Of course, we can stack like layers, yes, in encoder and decoder too, and we can make 2, 3, or 4 these bottlenecks, yes, this these units, yes, like Z1, Z2, but even though it's a really small bottleneck to provide all information, and that's why the coder couldn't represent accurately the translation of the input text. So, and that is why now all we want about Google Translator or even Yandex, yes, they work based on transformer models and transformer architecture. Yes. But we have to understand this model because seconds-to-seconds approach really popular, and we can it can inspire us for in many engineering tasks and to make something similar, not even with RNN. It can be transformer models, yes, or units, or even though. So that is why we have to understand it very well. So I think is it okay for for a small word about seconds-to-seconds, and I think we can start like a code. Yes, we have some data. For example, this is a multi 30K. It's a data set, yes, with some pairs of sentences. And we will try to make like the translator from German language to English language, yes. And yes, so, and this is how it looks like. Yes, we have in total about 30,000, yes, train examples, and this is we have like in German like zwei junge weiß Männer sind im Freien, yes, and etc. I forgot. My German is not really great, but we can read it in English. So yes, and we want to create a neural network which can make something similar. Yes, so, and that is what we want at the final of our seminar. So we will use an LTK tokenizer, like in the previous lesson, yes, because it's pretty simple for such tasks. Yes, I think of course, we could use something really great tokenizers, yes, like BGE, M3, or something similar. Yes, but for our tools, for our purpose, it's not really need to use such complex tools. I think when we go to the transformer architecture and transformer model, we will use it there because they're really necessary. So we'll tokenize our sentences like in this. I think you've already known this tokenizer. Yes, and so we make our was to lowercase, yes, and then strip it with our punctuation. So, and we, of course, we use it like in a one pipeline function. Yes, and here we can see like we have source, yes, in German, and target in English, yes, two sentences. But what's interesting? Let's move to the architecture of seconds-to-seconds. So imagine that we provide one sentences in German language, yes, like with the start of sequence token, yes, and then we begin our sentence like zwei males, etc. Yes, I forgot the whole sentence, but then we have end of the sequence, and then we make our encoder have to move all this sentence through this bottleneck, and of course the decoder have to begin with the first word. Yes, so if we have here zwei, the first word have to be two. Yes, but we have some problem that if we provide zwei, this word zwei, yes, in German, to the at the beginning of the RNN stake, yes, this layer, um, it can be so RNN can forget it, can forget the sense of this word or something else. So, and that is why it's really makes sense to reverse our German sentences, yes, our German tokens, and here to begin with the end of sequence, yes, and go like from last word to the first, because the first word will be closer to the bottleneck, and then of course the decoder have to provide this word, have to translate it, of course, first two. So it makes sense, and I think this you understand this intuition, so this engineering I think intuition of this approach. So let's did it. Yes, we reverse our source data set, so and we have something similar. Yes, so we begin with a dot, yes, and provide some words from the end of our sentences, and the end is the at the beginning of our sentence, like zwei Junge, etc. And we have so the target to Jan. So of course, everything is okay. So well create a vocabulary of our source and target languages. Yes, and which will base on one hot encoding for each token. So one hot encoding, I think you've already heard about this approach, this vocabulary, yes, but I will repeat. So it's when you have a vector of all zeros, yes, in the places. But the one position is represented like the index, yes, which equals 1. So and we can just make it with counter, yes, and vocab for the torch text input it. So and so let's make it, and here we have, for example, it's like vocab. I forgot how to about something. Yes, we have so like get item, I think, or something else. Get okay. Okay, I forgot which method. Torch vocab. Let's see in doc quotes items. Indexes. Okay. Well, I think. So yes, I forgot sometimes when you don't use vocab so really frequently, forgot some methods. So this is our source vocabulary, yes, and all words. Yes, we see this unknown token. Yes, it's we just about it in the future. So, but so we see our sentences, yes, with a lowercase, and they all split it in the word, and then it will be tokenized. Yes, but it's like each word, yes. For example, zwei will have like in one hot encoding, like 0, 1, and all zeros there to the end. So, well, yes, I think it's now you know. So, and unknown token, it's we have to have this unknown token because sometimes um, mm, we so we have no data in our trained data, some tokens, yes, which is in the test data or maybe in our inference. So um, we will convert it to the known token. And so first of all, we couldn't catch some exceptions and some warnings, yes. And then, of course, it can be great, maybe because it can be um, mm, some trash, for example, yes, from some emoji or something else, yes, something really real tokens or real punctuation. So and that um, have no semantic information. So for our um, sentences. So that is why we have to have a known token, yes, and we inserted to it, yes, and moreover we have to have some start of sequence and end of sequence token. It's special tokens which represent like start of the sentence, yes, and end of the sentence. And padding. Padding, it's we just fill with the padding tokens some sentences which is less than the maximum sentence vocabulary. So to put it in the one size, all these sentences will have the one size, and this one size will be the size of the maximum length of sentence in our one sentence, and then all these we can feel like a padding. So yes, now we can check our sizes for vocabularies. Yes, so we see so in the source vocabulary in German we have approximately 8,000 tokens, and in English we have like a bit less, so 6,000. So I think it's normal for German English language because German language have some articles. Yes, articles. I think I forgot this word like die, der, das, something else. Yes, and some maybe special these long words if you know German language. So when they use for describe something, they can connect two words like in one. So and of course describe something. That's why German language can be have more tokens, more words. So well, then we tokenize our sentences, yes, and here the example how we can tokenize. So we have like the positions, yes, of our tokens, yes, like two, yeah. So we have to, because the 1, 2, 3, and 4, these tokens have such number because it's the first sentence in our data set. So that's why they begin with these numbers. So they we can just check it, but it's the first. So but start of sequence and end of sequence we added after our vocabulary. So that is why they have so huge numbers. So and of course we impact so this in our encode function. And of course, you can notice then we reverse our source vocabulary, and start of sequence and end of sequence, they like change the sense, yeah, yes, of each other. But it doesn't matter because for our model, it's only the tokens, tokens with some numbers, and they just say for the model in the training stage, yes, in the training flow, that so look, here we just start with special token, and it's described the start of sequence, yes, start of the our sentence, and this token start defines the end of this sentence. And no matter, it doesn't matter, so that start of sequence, end of sequence, they represent something else. It's okay for our model, so it's it can train with it. So well, yes. Now let's let's move through our batches. Yes, to we write for batching our datasets, batching our or data. So for training. So and I think here it's nothing special. Just we use our pad sequence. Yes, we padding value with our pad token. Yes. So and if we need it, and then we just with a data loader function we create our data sets. Yes, for train data loader. Yes, and search target batch. So batch size we set like 256. So I think sometimes it's a bit bigger than usual. So usually I use 16.4 or 128, but it's okay for such a task. So, well, yes, and we created this the similar for the validation set, and now we built our Seq2Seq model. So, yes, we will use like 2 layers of LSTM. In paper, there were 4 layer LSTM, yes, 4 layers, but okay. And for our, I think for our task, it's 2 layers will be great, and it's enough. Well, let's explain. So we have our encoder. So we have like start of sequence. Yes, we have some input sequence. Then we have some 2 layers and 2 bottlenecks. Yes, token bottlenecks. So and we each unit of LSTM will provide so the hidden state. Yes, the input hidden state. Yes, and the output. So and some context with context here. We'll go here. So which arguments we have? So we have n tokens. Yes. So the number, the size of our vocabulary. Yes, and the number of tokens. Embedding dimension. So let's talk about the embedding layers a bit more. So I will provide you so something like this. So the source of the docs of PyTorch, yes, and embedding is the learnable metrics which provide some embedding vectors, yes. Similarly, it makes the size of our input, yes, less. And of course, in the language task, we have to have these layers because we couldn't work with large sentences, yes. And because, for example, you have maybe in German dataset, the largest sentence can be like with a, I don't know, like 30 words, yes, for example. And we have, first of all, we have some 30 numbers, yes, our tokens. And this number begins with the start of sequence and end of sequence. They're really huge values, like 5,000 or so. And we have only 30, yes. Other sentences, so they will be so less, but we pad it, yes, pad them. So that is why in the last part of each sentence have to repeat it tokens. It's not really great for understanding the sense and the semantic of these sentences. That's why we can provide and I think uppercase, yes, make this size of our dictionary up, yes, and embedding like the matrix which multiply input vector, yes, and in the output it can have, for example, 128 vector, yes, vector size. It's learnable, so it's of course, and it's initialized from a normal distribution, yes, 0 and 1, 0 mean, so 1 variance. So I think that's all. It's a really pretty simple layer, but I think sometimes so students don't really understand how it works exactly. So, and so we have like hidden dimension. I think you know about it because you have to understand like LSTM, their hidden dimension. So you can ask some questions if you don't understand something or you forgot something. Yes, it's okay. So if you, okay, I will do it in the future. So and layers, so of our NN, but of course it's two. So in dropout we have to stabilize our chainable process, yes, and we want to regularize. It's a regularization parameter, yes, for to prevent overfitting, because RNN, so they overfit really simple, really. It's because do somebody know why RNNs and LSTMs overfit so simply? So why? It's in architecture. It depends of architecture. I don't know exactly why. What's the purpose of the? No, I don't. So why RNN and LSTM to overfit really simple? So simply it's depends on its architecture, but maybe somebody knows why exactly it's really overfit. So simple, especially when we have like some not one layer of RNN, yes, or LSTM, it doesn't matter, or even two.
I think you mean you're asking why RN and LTSM overfits.
Yes, yes.
I think it's just because of the model complexity. And if the data isn't complex enough, it will just memorize it.
It's so general answer, but I think in RNN there's some special of architecture. Yes, why it's depends of it of this architecture, and there's some problems. So maybe you know.
Can you clarify what exactly are you like asking?
So
I don't quite get it.
yes. So I think I can explain just.
Wait, are you talking about the exploding gradient issue? I'm
Yes,
not
yes,
sure.
yes, exactly.
Okay. Okay.
That is why, like in RNN, simply we have one function. Yes, here is originally is tangents, hypertangents. Yes, tang. And in LSTM we have some units like sigmoid, tang, hyperbolic tangents too. Yes, and that is why. So sometimes it's really so simple to overfit it. Of course, it's maybe it's not a gradient explosion really, because these is functions, so not like the infinity, yes, not like ReLU, but it overfits really simply, really simple. That is why we need dropout layer. So okay, so I think if you have some question about encoder, you can ask it. So Okay, 3 to 1. Okay, let's move to this implementation. So here we have our embedding layer, then dropout, and then LSTM. So it's just initialize, yes. But in forward layer, we have some embedding, yes, and then hidden from ERNN. So that's all. And so let's decode. So of course, so here, if you notice here, we have only one layer of RNN. So because I think it's the simplest version of this notebook, and I think 2 layers will train pretty longer than this version, but it's okay for our purpose, for our learnable goal. It's okay. So decoder consists have some similar structure, but we have input our units from our bottleneck, and of course we have like a target text, yes, and we want to provide this target text depends on these units. So and in this decoder architecture, so we have the similar embedding layer, dropout, RNN, like LSTM, but in out we have our linear layer, yes. So for understanding, to create our output, yes. So we have here 2 embedding with and dropout layer, and one RNN layer, and then output. Yes, it's like predictions of our logits of the next tokens. That is why we have to have our linear layer, yes, on the output. So in a final, yes, in a final implementation, we have our model, which looks like here. We have some bottlenecks, but we have only one layer here, not 2. But it's of course, if you want to experiment, yes, or use this notebook like yourself, of course, you can just add here one layer, so just like this, and to make it like hidden from this to here, yes, from the input of our RNN, and embedded from the output. You have to create this embedded, and everything will be okay. So everything will be work. But of course, I want to warn you that the time of training, of course, it will increase. I think twice times. So I think that's all. That is what we did. Yes. So we create our model, and now we want to train it. Training is we of course put it together. Yes, in one class. So we here you see, yes, so our batch size, like target length, so it's etc. Yes, and here our training loop, yes, for first for the first time, yes, we have our decoder, yes, predictions and hidden layer, and press we just append, and we create our teacher force. It's when you put in the input of the decoder the target sentences. It's a great hack for training, yes, this sequence-to-sequence model. I mean, if maybe some of you noticed that here we have some input in decoder, and maybe you will ask me why, because we have our input on the German text, not English. We don't have English in the inference, and then we have to provide and move our German text through these bottleneck, and then we have the English text in the output. Yes, you're right. But in the training process, it's really great to help decoder to make the understandable text for it, yes, and to stabilize learning by adding sometimes in random factor, not really frequently, yes, the target sentence of the input. So for understanding how it should be. So we, in such hack, we can increase the quality and I think accuracy of our neural translate machine. So okay, so that is what the stage of quad do. Okay, so this is training. So we have our encoder, our decoder. Yes. Unfortunately, I have only CPU. So and we have to combine this in a Seq2Seq model. Yes. And here we initializing our weights of our model from like 0.08, yes, from minus to positive value, yes, in a uniform distribution. So, and of course we did it. So like init weights. So, but I want to tell you something new about weights initializing. Do you know about it? Something, I don't know, information about it? Do you hear about initializing the weights of the model? It's really
I'm, I mean, like, for example, in reinforcement learning, there is like this thing where we initialize our like policy with a policy prior. I think it's similar for weights, where weights are like the checkpoints.
yeah, you're quite right. You're quite right. And I want to show you something else about initializing the weights. It's the Yandex handbook here in Russian. So, but I mean, that is here. So, I just so here you see that we initialize our weights of our model by uniform distribution. Of course, it is not really good in a, like in general, yes, because we have so many types of initializing, and I want to show you that initializing like in a random unit, random, it's work better than we make only zeros. Yes, it is okay. It's okay. I think it's makes sense. You understand why it work better, because if you all your weights like zero, you couldn't compute the gradients. So if you couldn't compute the gradients, if all your weights will stay like near zero. So which is why saying uniform or normal distribution, you have to initialize like in a random. But random, it's not only this approach. You have some Xavier or normalized Xavier initialization. So it especially work great with hyperbolic tangents activation functions, because in this approach, in this initializing initialization, I'm sorry. So so there this initializing, so it based on the symmetric function of activation by zero. So the tangents is the such function. So Xavier initialization or normalized Xavier, yes, it really fit better, and I think the best for tangents. So and you have some here the differences, yes, between activation with some standard, yes, and normalize initialization. So in hyperbolic tangent. So you see, so here we from layer to layer, our distributions don't change. It's better. It's better, of course. So there are some coming initialization for ReLU, yes, but I think it's we will see it in the next step when we will work with ReLU initialization. So let's move to our notebook. So so we have in our model we have approximately 14 million trainable parameters. So it's okay for such model. So we will use Adam optimizer. So and cross-entropy loss for our criterion. And well, here we have our training loop. Yes, we did like 15 epochs. Yes, of course we use like clipping the gradient to prevent its explosion. Yes, and here you can see the result. So it's actual translation, of course, from German language to English. So you can see, so the target, yes, it's not really similar like a prediction, yes, but our hack with reversing sentences, yes, in the beginning of the encoder part, it works. So we see here like the similar words, but then something go not so well, yes, and of course we have some not really great sense. Here we have the duplicating some words. It happens with Seq2Seq models, yes, and but generally we can see the great sense, yes, and sometimes really sensible translation at the beginning of the sentences, yes, of the predictions. But when we go to the end of the sentences, yes, we can see some strange words repeated, some articles, yes, some strange words, so and etc. That is why that's the great minus of Seq2Seq approach. So that at the beginning we have really great, yes, a little boy, a young boy, yes, a brown dog is running, yes, with a black, another white dog, but after the black dog here, yes. But at the end have some not really accurate translation. That is why people use transformer. That is why Google Translate use transformer architecture and more, I think, powerful models. Okay, for neural machine translation, that's all. I think we can just move to your questions about seminar, or your questions about maybe lectures. Maybe you have it. So, well, don't hesitate. You can ask me. Well, yes. So what if you don't have any questions? So I really advise you to see something about sequence-to-sequence materials. For example, you can read some maybe Andrew, yeah, or maybe Hugging Face or Andrew In. Yes, I think it's really makes sense, and it will be help you, of course, for understanding our course in the next lessons. So maybe this, yes. So something like these blocks, so you can see, but I really am not sure. See something. Yes, so somewhat like these tasks, yes, like these videos, or maybe like a Medium. Just read it. So when if you want to know something better, so and what's more, I think we in the next seminar, or like we go to the transformer architecture. So if you don't know transformer architecture, so for example, self-attention, yes, what is BERT is, or GPT model, maybe you know, I don't know. I really advise you to read like a couple of words about it to understand it better, or to see some lectures about these topics. So for today, I think that's all. If you don't have any questions, so we can finish. If you have, so don't hesitate to ask me. So, well, thank you for this lesson.
Thank you for the lecture.
Yes, thank you too. Thank you too for coming. So goodbye.
Thanks for the lecture.
Yes, goodbye. Goodbye, guys.
Thank you.